I want to take a moment to thank my very special Patreon supporters, Antonio, Chif1, Patrick, Michael, and Afshan. This channel would not be possible without them. Please don't forget to subscribe, hit the notification button, and join me on Patreon. Thank you very much. We are done with constructing the real numbers, and now we are moving on toward complex analysis. But before we can do that, we need some multivariable calculus, because in order to prove the results in the basic results in complex analysis, we need Green's theorem, which is multivariable calculus. So in this video, we're just going to take a leisurely stroll through calculus and what it is and what the issues are, and some different topics that will prepare us for the fundamental theorem, which we'll do next week, and then we'll move on to multivariable calculus. In order to start that, we're going to go through multivariable calculus carefully. And as I've said before, we sort of, with these videos, we have to kind of decide where we want to all be on the same page. And I had to pick some kind of a level from which we can start. I'm assuming that everyone's had calculus, but I'm not assuming anything beyond that. And so we're going to start today with the fundamental theorem of calculus. So what is calculus? Calculus is all about limits, and it follows directly from what we've been doing with real numbers. You remember we had sets that were where p squared is less than 2, and then you could get closer and closer to it, but without ever going over the limit, and so on. And calculus is sort of the application or the further exploration of this. Now, what's interesting about that is that our motivation for constructing the real numbers came from a completely different realm. It came from polynomials. Because if we have polynomials with coefficients that are rational, then very quickly we can come up with a polynomial that doesn't have a solution in the rationals. And in order to solve an equation like this, we needed to add something more to the rational numbers, and we ended up with the real numbers by adding the least upper bound property to the rationals, and then that gave us the real numbers. So what's interesting is that in a way, real numbers sort of stand at kind of like this nexus.
I already had an IQ test this year.
Between algebra on the one hand and then real analysis and complex analysis on the other hand. And we can go two ways with this. We could go back, as I did last week, and look at Galois theory and groups of permutations and things, which we'll have to get to. Or you can go forward now that we have the real numbers and do things with complex numbers and real numbers, which is what we're going to do for now. So on the one hand, there's the solutions to polynomials like this, but on the other hand, there are other problems that have been around forever which are not about algebra necessarily, but there's questions that are like the classic calculus questions, like what is instantaneous speed? Right? Because we know that if you go 30 miles and it takes you an hour to do that, then you're going 30 miles per hour. But if you get in your car, speedometer says you're going 30 miles an hour. What does that actually mean? Because you're not even going to be gone an hour. It means that at this instant you're going that speed. Your position is changing at a rate of 30 miles in 1 hour, even though you're only going for a few feet per second, and then smaller and smaller. So if you have a graph, and then this is the rise over the run, and then as this gets closer and closer to this point, you'll get the slope of this line, which is the tangent of this graph, or the instantaneous speed if this is a position graph. And then another problem that's been around forever is the area under a curve. So for instance, if you have a cosine and you're wondering what is the area here from 0 to pi over 2, and it turns out quite insanely, the area here is 1. Using calculus, we can see that that's true because if we have from 0 to pi over 2 of cosine, the antiderivative of cosine is sine. From pi over 2 to 0 is the sine of pi over 2 is 1, so it's 1, and the sine of 0 is 0, so it equals 1. What an insane thing this is. They actually were able to solve this problem without calculus. And if you try to wrap your mind around that, I don't even know how, I can't imagine how you would begin doing it. So they were interested in these things, and area problems were one of the things they were interested in. Instantaneous speed and tangent problems were another thing they were interested in. And the interesting thing is, for a long time, they didn't even realize that these two problems were related. They don't seem related, right? I mean, I just repeated, one is about area and one's about the tangent line. What do those two things have to do with each other? It took them a long time to figure out that they are in fact related. So the fundamental theorem actually is what makes the connection between instantaneous speed and area, that in fact these are inverse functions. And then what we're working toward is complex analysis, because it turns out we need complex analysis in order to solve Fermat's last theorem. That also sounds bizarre because that's just simple algebra, right? The Pythagorean theorem. But that's what the statement that elliptic curves are modular forms. Modular forms are in complex analysis. And as I mentioned once a long time ago, once we get to complex analysis, we'll see that there's this insane way that elliptic curves fall out of complex analysis as well. So that's where we're getting to. So we really need to understand complex analysis. So this is where we're going. Now, another thing is we do this, and one of the goals or philosophies of these videos, in my own philosophy about math from the beginning, has been that nothing is beyond comprehension if you break it down. And actually, you'll even see people ask this, like on Quora, where people say, no, there's a certain level of math where you actually can't break it down and make it understandable. I don't buy that, but we'll see when we get there. So far, what we're doing is definitely comprehensible, but the books tend to skip steps. So we're not skipping steps. We're going to understand it and not hand wave and not learn these things mechanically. And calculus in particular, I think a lot of it is taught mechanically. A lot of what we learn in freshman calculus is how to do things without really understanding. At least that's the way I learned it. Like, I learned that the integral is the area under a curve, and I understand why. And I understand that the derivative is the tangent. I understand why. I don't really understand from class why they're related, but I know that you can figure out the area under the curve by taking, subtracting one value from another and so on. We're going to do better than that here. Okay. So the derivative, to me, seems pretty straightforward. It is what I think you think it is, or what it seems to be. You have a graph, and you want to know the tangent here, and well, you know that the slope from like this point down to here is just this distance divided by this distance, right? So you take these two, subtract them, and then this distance, subtract that, and you have this slope. So then if you move this point closer to this point, then the tangent is going to slowly get closer and closer to this slope is going to get closer and closer to the tangent as the intersection approaches that point. And that's all the derivative is. It's just the slope of a line, the rise over the run. So in this case, if we make this distance h, this distance, then we have from x to x plus h, right? And then this distance would be f of x plus h and f of x. So if we wanted the slope of this, it would be f of x plus h minus f of x over, we could either say x plus h minus x, which is h. Okay, that would be at each h. So then as we let h get closer and closer to 0, just take the limit as h approaches 0, and that is the derivative of x. So when you're learning this, the only thing that I think is hard to believe, and this I think is one of the things that I don't think is taught well in calculus, is the whole idea of dividing by 0. The truth is we're not dividing by 0. We're never dividing by 0. It's approaching 0. It's getting closer and closer. And what we've just been working on is that you can get as close as you want. You can, no matter how close you get, you can always get closer without ever reaching 0. And as long as it's not 0, you can always divide this, but you can get arbitrarily close. And a lot of people think of this division as being an infinitesimally small number. It's actually not infinitesimally small. That's the whole point of the Archimedean property, which said that for any x and any y, you can find an n such that nx will be greater than y. And the point of this is that no matter how small x is, there's no such thing as an x that's, I mean, as long as x is greater than 0, there's no such thing as an x that is infinitesimally small. If it's not 0, then you're always going to be able to multiply it by something and get arbitrarily big. That's what the Archimedean property is. That's what we're doing here. We're getting arbitrarily small, but we're not actually dividing by 0. So this same concept applies to integrals. We're told that an integral is the area under a curve. And then you slice this up into ever smaller pieces. If you have, again, x and x plus h, then this is f of x plus h. This is f of x. So as h gets closer and closer to 0, then the area of this rectangle will be closer and closer to f of x. F of x plus h and f of x is going to be somewhere in there, and it kind of squeezes as it gets closer and closer. Then you add all those up, and you have the area under this curve. And the point is, again, we're sort of taught that if you somehow add together a bunch of things that are infinitely small and you get a number, it's not what you're actually doing. It's actually, again, a limit. You're getting closer and closer to 0, but never actually multiplying by something that's infinitesimally small. But I'm going to talk more about this area thing because this is the other big thing. We're going to think of the area not as the area, but as total change. But first, so the definition of integral is, it's much more complicated. But the integral from a to b of f of x dx equals the limit as n approaches infinity, the sum of I equals 1 to n of f of x star I delta x, where delta x equals b minus a divided by n. So this means you're taking this interval and dividing them up by bigger and bigger numbers. So the slices are getting smaller and smaller. So this is the width of one of those intervals as n gets bigger. And x star I is a sample point lying within the interval of x to the I minus 1 and x to the I. So this is just ugly. And all it means is what we're talking about here, that you take, this represents the width of the slice, and then you're taking the function somewhere in here between the two edges of the slice, the value of f there, and you're multiplying it by the width. That gets you the area under this rectangle. That's what the integral is. Okay. Now let me make one more comment here about calculus, that it can be a problem as we go forward. But I want to talk about the notation, dy over dx and the integral of f of x dx. We think of this representing a fraction, the ratio of the rise over the run, right? The change in y over the change in x. And then we start thinking, well, so if we multiply both sides by dx, then you end up with this. And then you just take this thing and move it over there. That all makes sense. That's all algebra. Furthermore, if you want to do a change of variables, if you have dy over dt, you multiply that by dt over dx, just cancel the dt's, and you get dy over dx. That all works very well, and it looks very good, but it's not true. Dx is not an object that you can actually manipulate in this way. Dy over dx means the derivative of y. And this is just an operator. It's much more like a plus or a multiplication than anything else. It just says we're taking the derivative of this. So it's really the same as just using the apostrophe notation. That's what d over dx is. And then the same thing is true with integration. We have that f of x, that the integral of f of x dx, we're taught that that means that we're multiplying f of x times dx. And then we're summing that as dx gets smaller. That just isn't actually true. This is all one symbol. And all the dx is doing is telling us that's the variable that we're sort of sampling over in order to sum the changes. It's not the same dx here, and it's not an object at all, and it doesn't mean that it's the samples of x. And this is all one symbol, which means integrate f of x. And also, again, it's also thinking about this, if we're told that the integral is the area under the curve, then again, this seems to make sense because this is the width, this is the height, you add those together and you have the integral, which it works, but it's misleading in terms of what's really going on. And as we go forward in multivariable calculus, we're going to see, for instance, things like this, the square root of dx squared plus dy squared. What in the world does that mean? We'll also see this written as just as ds. So we'll see something that's like ds, which then represents this, but that looks like then we can manipulate the dx and the dy. We really can't. Both of these are just telling us what it is that we're going to be integrating over, how we're slicing it up to sum over it, okay? And so to show you that I'm not making this up, most calculus books actually do say they do tell you what I'm telling you here. They just don't make anything of it. It goes in one ear and out the other. But I just want to read to you what James Stewart says. Here's what Stewart says about the differential operators d and d over dx. He says, the symbols d and dx are called differential operators because they indicate the operation of differentiation, which is the process of calculating a derivative. The symbol dy over dx, which was introduced by Leibniz, should not be regarded as a ratio. It is simply a synonym for f prime of x. Regarding this, he says the same thing. When he's talking about integration, he says, the symbol dx has no meaning by itself. The integral from a to b of fx dx is all one symbol. The dx simply indicates that the independent variable is x. So the reason I think that the integral is taught as the area under the curve is that, as I've shown you, as I drew, it's much easier to understand it in that way. You're slicing it up, taking one point in here, multiplying the height times the width, you add those up and you have some approximation of the area under the curve. But then when we go higher to higher dimensions, that doesn't seem to make sense at all. So what I want to do is just start looking at the integral, ignoring the area problem altogether, although it works for the area problem, but we're going to ignore the area problem and look at it instead as total change. They teach us that the integral is the area under the curve, but then almost immediately you start asking questions that picture can't answer. Like, what happens if f goes below 0? Then there's this, and the integral of this would be 0 because half of it's positive and half of it's negative. Well, what the heck is negative area? It doesn't even make sense. If you think about it as total change, it completely makes sense because the change starts out positive and then it goes down to 0 and then it slowly becomes negative so that by the end of the graph, the total change is 0. And then the advantage that looking at the integral as total change has is that the derivative is rate of change, the integral is total change, then it's much easier to understand why they're related. So just to think about this for a minute, to total change. What does total change mean? If you're in a car and we're going 60 miles per hour and we drive for 2 hours, how far have we gone? Well, we're changing our position at a rate of 60 miles in each hour. You multiply that by 2 hours and you have the total of 120 miles, right? That's straightforward. So if we think of s as a position function and v is the velocity function, then the derivative of s equals t, because this is the rate of change at any time t. This is how much s is changing from one moment to the next at time t. So if you wanted to know your change in position from time t1 to t2, you could do that by adding up the rates of change during the time period. So we went 10 miles per hour for 6 minutes, 60 miles per hour for 60 minutes, and then we stopped for an hour. So how far have we gone? Well, we went 10 miles an hour. This is 1/10 of an hour. So that would be 10 times 0.1 plus. Then we went 60 miles an hour for 60 minutes. So that's 1 hour. So that's plus 60 times 1. And then we stopped plus 60 or plus 0 times 1. So it totals 61. So we went a total of 61 miles, right? Our change in position was 61 miles. So this is an obvious thing. Like this is something that you would do if you're driving somewhere. We were in town, we were only going 10 miles an hour, then we got out on the highway, then we stopped for lunch. How far have we gone? You can figure that out without looking at the odometer or without looking at where you are by calculating the changes. We went 10 miles an hour for 6 minutes, 60 miles for an hour, and then we stopped for an hour. So we had to have gone 61 miles. This is the sum of the rates of change, right? We could also figure this out by looking at our position at T2 and our position at T1. So if we started at mile marker 0, and if at the end of the time we looked at the mile marker here, it was 61. So if we want to know how far we've gone 61 minus 0, we've gone 61. That means that the total change that we went through was S2 minus ST1 equals 61 minus 0 equals 61. So just looking at, if you just think about a real world example, this is pretty straightforward, that you can calculate how far you've gone by, you keep telling me how fast I'm going every minute, and I'll write it down, and then I could calculate where are we now. Or if you just tell me where we are at the end, tell me where we were at the beginning, and I'll be able to tell you the total change that we went through, right? Which is what we did here. We were changing 10 miles an hour per hour for a while, then we were changing 60 miles an hour for a while. You add all those up, and the total change was 61 miles. So, or by subtracting the end from the beginning, the total was 61 miles. So then if you think about it, this is just kind of chunky, but in real life, of course, we had to accelerate from 0 to 60 or from 10 to 60 and then slow down. So it's not going to be, we could slice up the differences finer and finer, and it's probably not going to be quite 61. But if we had instantaneous speed at each moment, added all those rates of change up over the time, we would end up with the total amount that our position changed. And again, we could also just look at where we were compared to where we started. Same thing, okay? So when you look at the integral as the summing up of the rate of change, it also makes sense. So to put this together then, if you had T1, T2, you took the integral of the velocity during that time, you can see that it would be S2 minus S1, right? This is the fundamental theorem of calculus, which is what we're going to get at. Now, if we graphed the velocity here, we went along for a little bit at 10 miles an hour, then we went up to 60 miles an hour, and then we went down to 0. This would be VT. But if we graphed the position, we're starting at 0, we're going along just a little bit, then we're going way farther, faster for a while, and then we completely stop. And then you can see that if you just subtract this one from this one, you'll get what amounts to the area under this curve. So the amazing thing about this is that it doesn't actually matter what speeds we went in here. All that matters is where we started and where we ended. The reason for that is also clear if you think about it. We could floor it, go 100 miles an hour for 20 minutes, then slam on the brakes, put it in reverse for 10 minutes, then floor it again and go 100 again. And if we add up those changes, they're still going to come out to where we ended from where we began. So the interesting thing is that these two endpoints are enough for us to know the total change, no matter what is going on in here. It could be this, it could just be this or this. It doesn't matter. The total change is what matters, as you can see, and how we got there doesn't change the total, because what matters is where we ended from where we started. And if we see integrals in this way, then it makes multivariable calculus make way more sense, because Green's theorem, which is the one that we're working toward, says
if you have a two-dimensional plane and you have a closed path around that plane, Green's theorem tells you that if you add up what's going on the boundary, that will equal taking the integral of the derivatives inside. So it works exactly like one-dimensional integrals. With one-dimensional, you add up the endpoints, and that's going to equal the integral of the derivative inside those endpoints. The same thing with Green's theorem. You add up all the derivatives inside the area is equal to adding up what's going on the boundary outside. So we see that multivariable calculus is the same as single variable calculus in terms of this relationship. So in other words, this thing that we've been looking at, where if you just look at the endpoints, you can tell what's been going on in the middle, that you can look at the total change by looking at the endpoints. It's the same as in multiple dimensions. If you look at the change around the boundary, that equals the total change that's going on inside the boundary. So in complex analysis, it's even more interesting because there's a relationship between the partial derivatives inside the region called the Cauchy-Riemann relations, which place even stronger restrictions on the behavior inside the region. So if there are no holes inside the region, that means that when you integrate around the boundary, that sum has to be 0. So that fact then is what makes complex analysis so interesting, because starting with that fact, then you can start counting the holes and so on.
And when you first hear this in complex analysis, it's completely bizarre that if you just go around something, you can figure out what's going on inside. But if we understand this point, how the two endpoints tell you something about what's going on inside, then it makes a lot more sense. Okay, so I'm going to stop here for now, and next week then we will prove the fundamental theorem of calculus, and then we'll go on from there. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.